Hello, everyone. In this video, I will give you a quick review on linear algebra. So I will go over some of the basics, some properties, and I'm gonna end with matrix differentiation. All this because the video is meant to help students taking econometrics, especially with multivariate regression. This is because when you run linear regression models with multiple variables, it will be way easier to work with matrix notation. So convention in linear algebra is to use uppercase letters to denote matrices. This example gives you a matrix A that is defined by these elements: A11, A12, A21, and A22. The subscripts of each of these elements determine the position of the element itself. In particular, the order is always in terms of rows and columns. The first subscript refers to rows, and the second subscript refers to columns. That's why element A11 is positioned in first row, first column. Element A2 is positioned in the first row, second column, right? That makes sense. The element A21 is positioned in the second row, first column, and A22, second row, second column. Okay. This matrix has dimensions 2 times 2. The dimensions of the matrix also follow the same order, rows and columns, 2 rows and 2 columns. The first property, or let's say operator, that we are going to learn is the transpose of a matrix. Some people use a T. I'm going to use prime. A prime refers to the transpose of matrix A, which in this case, the only thing that we are going to do is to transform those rows into columns. Or you can see it in the other way around. You're going to transform those columns into rows. Let me start with the first row. I will make it a column, okay? So I will say the first column now will be the whole first row. And that's it. That's all you do. And you can do something similar, but for my other row, which is this one, which means that my second new column is now going to be A21, A22. And that's the concept of the transpose of a matrix. Your only changes rows for columns. The other concept that I want you to remember is the one of the product of two matrices. Suppose that we have matrix A and matrix B. Matrix A is the same one that we already defined. Matrix B now will be this one with elements B11 for first row, first column, B12 for first row, second column, and so on. There is one condition in order to perform the product of two matrices. And the condition is that the number of rows, the number of columns in your first matrix, in this case, 2 columns, must correspond with the number of rows in your second matrix. In this case, of course, since both matrices are have dimensions 2 by 2, it is obvious that we are allowed to perform the product because the number of columns in matrix A correspond to the number of rows in matrix B. The product also is simple because it follows a specific order. And the order is that the element in the first row, first column, comes from multiplying the first row in column A and the first column in matrix B. Let me mark this in the corresponding matrices, and you will see. So you see how it makes sense? Is that this is the position 1, 1. One row, row 1, column 1. So you have to multiply row 1 of your first matrix times the first column in your second matrix. In this case, the multiplication will be A11 times B11 plus your other elements, A12, B21. And that's it. Now, you may guess it that clearly for the next element, first row, second column, we're going to do something similar. First row of matrix A and second column of matrix B. It's exactly in a very specific order. So the first element is A11 times B12 plus A12 times B22. Here I will close the parentheses. And let me erase this part where I highlighted the elements of the matrix. So what comes next is the second, let's say the third element in this matrix is second row, first column. Second row of matrix A, first column of matrix B, which means that this is A21, B11 plus A22, B21. And finally, we will continue working with the second row in matrix A, but now second column of matrix B, which is A21, B12 plus A22, B22. And that's how you perform the product of two matrices. Just remember, what is important is that there is a coincidence in the number of columns of the first matrix and the number of rows of the second matrix. That part is key. The other part of the process makes sense and is easy to perform because you only have to follow the order, no? The order of the positions of the elements of the product of the matrices. But other than that, honestly, this should be straightforward. Now that you know this stuff, so those are word operators, the transpose and the product of two matrices. Let's work with some properties, just quickly. And the first property refers to the transpose of the product of two matrices. So suppose that you have matrix A times B, and this is something that you want to transpose. You can apply the transpose to each of the matrices, but you have to flip the order of the matrices. B transpose, A transpose. Second property, suppose that instead of the product of two matrices, you want to transpose the sum of two matrices. Oh, by the way, if you want to sum matrices, the dimensions must be exactly the same in terms of rows and columns, okay? It's even more demanding than the case of the product. And the transposes can easily apply to each of the elements of this sum. So you don't need to flip anything. It's just A transpose plus B transpose. So that one was easy. And the last property in terms of the transpose of a matrix is, suppose that you have A transpose and you transpose this once again. Obviously, this will give you A, not transpose, just A, the original matrix A. Well, now that you have this clear, let's go and explain a new concept. Let me define what we know as the identity matrix. The identity matrix is a square matrix. Square means that you have the same number of rows and columns. So it's a square matrix with only ones in the main diagonal and zeros above and below the main diagonal. For example, you start with 1, your second element is 0, 0, and then you continue in the same fashion. In the second row, you will have 0, 1, 0, and then you continue with zeros. You will continue the same way until you get to 0, 0, 0, and you will continue, but now you will end with 1. So you only have ones in the main diagonal and zeros above and below the main diagonal. Which means that obviously you may have the case of the 2 by 2 identity matrix, which is just 1, 0, 0, 1. So why is this important? Because the identity matrix is similar to the concept of the number 1 in real numbers. Which means that if you have a matrix A and you multiply this matrix by its inverse, that will give you the identity matrix. Probably something that, like an additional property that I should explain here, is that A is equal to A transpose if A is symmetric. If A is a symmetric matrix, the transpose of A is A itself. Now, at this point, you may wonder what's the inverse of a matrix. And I'm not going to teach you the actual formula to obtain the inverse of a matrix. Instead, I will show you the easy case, which is the inverse of a 2 by 2 matrix. This will kind of give you the idea, the actual process to inverse any matrix from other or higher dimension is a little bit more complicated, but for the easy case of the 2 by 2 matrix, it's as follows. So suppose that you will still working with the original A matrix that I described before, with elements A11, A12, A21, and A22. This is the matrix from which you would like to compute the inverse. So the formula is the following. You will multiply a matrix by the inverse of the determinant of that matrix. And here in the main diagonal, you will flip the elements. See, that's the only thing that I did. And you will change the sign of the other elements that you have above and below the main diagonal. And that's it. This is the formula that you will use to inverse a 2 by 2 matrix. Now, of course, here at this point, you should also ask, what is the determinant of a matrix? Well, the determinant of a matrix comes from cross-multiplying the diagonals of the matrix. So the main diagonal comes first, A11, A22, and you subtract the multiplication of the other diagonal, which comes from A21, A22. Sorry, A12, A21. Exactly. That's the way. And I'm going to finish this video with matrix differentiation. Matrix differentiation. And I will start with some properties. Just as you learn calculus in high school, there are particular definitions of the derivative of the product of a matrix and a vector x when you take the derivative with respect to that vector. And just as you learn in calculus, this is equals to the constant that was multiplying your variable. In this case, we don't have a constant. We have a matrix A that was multiplying the vector x. No? So the derivative of A times x is just A. The second property tells you that maybe what you have is the product of a matrix and two vectors. No? And if you want to take the derivative with respect to vector x, well, this is pretty much like in calculus. It's just y transpose matrix A. But here it comes the interesting part. What if you have the exact same product, y transpose A x, and you would like to take the derivative not with respect to x, but with respect to y? Not with respect to y transpose, with respect to y. Since y is transposed in the original product, and you are taking the derivative with respect to y, you will use a similar property as in the second property, but you will have to transpose the remaining elements, which means that you will have something like x transpose A transpose, right? The fourth property is also something that you will use when you learn multivariate regression models. And this is the derivative of x transpose A x with respect to x. So this is like analogous to the case when we have the derivative of a constant multiplying x squared, no? Something similar. Well, here you will use the same properties that we described before, but you will multiply x transpose by the sum of A and A transpose. But know that if your matrix A is symmetric, meaning that the transpose of A is A, then simplify your derivative as 2 times x transpose A, which is pretty much like the case of x squared when you use derivatives. No? If you derive the function A times x squared, that's basically what you get. No? So you have a similar case in linear algebra, but only if A is symmetric. Otherwise, you will have to multiply your x transpose by A plus A transpose. But lucky you, the matrix that you will work with when you derive the OLS estimator with in matrix notation is a symmetric matrix. and you will see that. Okay, so I don't want to make this video too long, so I think this should be enough for you to work with multivariate regression models in matrix notation with all these properties and the previous notation that I introduced. All right, so I hope this video was useful, and see you next time. Peace.